Alright, in this video I'm going to go over the basics of weak acids and weak bases. So the first thing you have to get comfortable with is writing an equation. So when you have just an acid or just a base, and it's a weak acid or weak base, you need to write the equation when it dissolves into water. So it's actually going to be reacting to the water when you have a weak acid or a weak base. So I'm going to pull up the white screen, and then we will work on writing these equations out. Alright, so the first one is acetic acid. This is an important one for you to get used to writing the formula out because it is used all the time. Acetic acid is also known as ethanoic acid. Alright, so acetic acid, well, acetate is this, CH3COO, like this, -1. It can also be written as CH3CO2, or it can even be written like this, C2H3O2. It's all the same thing. It just depends on who's writing it or whatever it is. So either way is actually correct. So this is acetate. Well, acetic acid is going to have acetate and a hydrogen ion in it. So remember, if it does not have a hydro prefix, it's hydrogen and some polyatomic. So acetate in this case. So when we write out the formula for acetic acid, you can write it like this, or more typically it's written like this, CH3COOO, because the hydrogen will end up bonding to the O right here. So when we write out this equation, we're going to have acetic acid, and it's going to dissolve into water. But remember, weak acid or weak base is actually going to react to the water. So since this is an acid, we are going to remove a hydrogen and then add it to the water. So we're going to make hydronium. So anytime that you have an acid and water, you're going to make hydronium. And then when you add the hydrogen here, you're taking it off here, so you're making its conjugate. So you're going to be taking off an H+. So it should become acetate at that point. So that is the equation. So remember, whenever you have a weak acid or weak base, and it's necessary to look at an equation, it's actually reacting to the water. It's not just simply breaking apart. The hydrogen ion will actually get either removed from the acid or added to the base, and then it interacts with the water that way. Alright, so let's look at the next one. It's propanoic acid. Alright, so propanoic acid, they gave you the formula CH3, CH2, COOH. Okay, so it's reacting to water, and it's an acid, so this acid will be removed, and then it will create hydronium, H3O+, and then what we're going to be left with is its conjugate, so propanoate. You're going to basically just remove a hydrogen ion, and then it becomes this. Alright, so now let's look at a base. Let's look at ammonia. Ammonia is NH3. This is another thing that you need to know this one. And you're going to add it to water. Okay, so anything, typically when you have nitrogen in a compound, typically it is going to be basic. Because when I draw out this compound right here, if I draw the Lewis structure, what I end up looking at is I have a lone pair right here. Well, that lone pair can attach to a hydrogen ion, and it's attracted to it. So that lone pair from the nitrogen actually can pull in a hydrogen ion. So anytime that you see amine in the name, or if it's ammonia, a lot of things with nitrogen are usually going to be basic. Alright, so if it's a base, that means a hydrogen ion will get added to it. So that means that I'm actually going to remove the hydrogen from the water and add it to the NH3. So NH3 becomes NH4. I'm adding a hydrogen, and since it did not have a charge, well, I'm adding an H+, it becomes charged with a +1. Then, because it's a base, I'm making hydroxide. I should have hydroxide in my solution. So acids make hydronium, bases will make hydroxide. All right, let's look at another one. Let's look at methylamine. Methylamine is another popular one. Methylamine is NH2 CH3. So we're going to add that to water. And this is a base. You can tell because it says amine in the name. And also you've got that hydrogen ion, or that nitrogen atom right there. So that means that the hydrogen can get added to this nitrogen right here. So anytime that you have an amine group, the hydrogen typically gets added to the nitrogen. So let's do that. Let's remove a hydrogen and add it to the nitrogen. So it should be NH3. I'm going to have 3 nitrogen or hydrogens bonded to that nitrogen now. CH3, and I'm adding an H+, so it becomes positive. And I'm removing the hydrogen from the water to make hydroxide. So remember, if it's a base, I'm going to make hydroxide. If it's an acid, I should have hydronium in my solution. All right, so next one is hypochlorite. Hypochlorite is ClO-. Well, I can look at this and tell automatically this cannot be an acid. There's no hydrogen here at all. So there's no hydrogen to donate. So it has to be a base. So that means, again, I'm going to take off a hydrogen, and then I'm going to add it to the base. So it's going to become HClO, was a -1, so -1 plus 1 should be 0. And then I should be left with hydroxide. All right, so remember, anytime that you have a weak acid,
Brianna Gracie, please report to the main office. Brianna Gracie to the main office.
anytime I have a weak acid and I put it into water, I'm going to create hydronium. If I have a weak base and I put it into water, I'm going to make hydroxide. So really, you're just moving the hydrogen around in these reactions. All right, so now when we're dealing with a weak acid or weak base, we need to look at the K expression, because there is a K for weak acids and weak bases when they ionize into water. So K is the equilibrium constant, so Ka is the equilibrium constant when an acid is ionized into water to make hydronium. So if you have a large Ka, that indicates a stronger acid. So a Ka larger than 1 should be a strong acid. Kas are smaller than 1 will be weak acids. So when you have a weak acid and you put it into water, you're going to make some hydronium and some acetate. But if it's a weak acid, you'll only have a small amount of hydronium and acetate. So a large Ka indicates I'm making lots of products. Well, this is our reaction right here. And if I have a small Ka, that means I'm not going to make as many products. So that means I'm not going to have as many hydronium and acetate ions. I'm going to have more of just the weak acid in the solution as a whole. All right, so the Ka expression should be the concentration of the products divided by the reactants like we normally do. And that's hydronium, and whatever the conjugate is, this is our conjugate base, divided by our weak acid. So if you see Ha, that's some weak acid. That is a weak acid. And since H2O is a pure liquid, we do not put it into the K expression. So remember, pure liquids, pure solids do not get included into K expressions. So if you notice, for every one of these, I make one hydronium, and that's pretty much true of all acids and bases. Usually only one hydrogen will come off at a time. So usually everything's going to be a 1-to-1 ratio, which makes the math a little bit simpler. All right, so pKa is very, very similar to pH, and it's used as a way to express how strong an acid is. So pH is used to express how concentrated an acid is with hydronium. pKa indicates how strong the acid is. And it's just easier to use pKa because it's a whole number instead of a really, really tiny number, like 1.0 times 10 to the negative 10. So pKa is just a little bit simpler to use. It indicates how strong the acid is. The lower the pKa, the stronger the acid. So you can get pKa almost the same way that you get pH. It's the negative log of the Ka. But remember, it's still not the same thing as pH. pH is how concentrated an acid is. And this is how strong an acid is. So the smaller the pKa, the stronger the acid. All right, so let's work out an example. So if ethanoic acid has a pKa of 4.74, what is its Ka? Is it a strong acid or a weak acid? Okay, so we have a pKa of 4.74. So we want to know its Ka. Well, I know pKa is equal to the negative log of Ka. So I want to get Ka, so I just plug it in the equation. So I don't need like a reaction written out. I can just simply plug it into this simple equation. So 4.74 is equal to negative log of the Ka. Okay. Let's divide out the negative. It's times negative 1. So negative 1 times divided by negative 1 just gives me positive. So it's going to be negative 4.74 is equal to log of Ka. So what I did here, I just divided out negative 1. So I need to get rid of my log. Well, you're not dividing by log. Log is its own function. If you look on your calculator, the second log button should be 10 to some x. This is the anti-log. So that right there is the opposite of my log. So if I plug this in the calculator, I'm going to get a Ka of 1.8 times 10 to the negative fifth, and no units for K. So is it a strong acid or a weak acid? Well, the lower the pKa, hold on. All right, so we were trying to decide if this is a strong acid or a weak acid. Well, when we look at it, the pKa was 4.74. The Ka was equal to 1.89 times 10 to the negative fifth. Well, just looking at the Ka, I should automatically know it is a weak acid because it's less than 1. So basically, the smaller and smaller the number gets here, the stronger the acid. So once I get to a number that is at least 1 or greater than 1, I'm going to get to negative numbers. So the closer it gets to a negative number, the closer it gets to 0, and below that, that's going to be a strong acid. So those are going to be strong acids. So the closer it is to 0, the closer it is to 0, the stronger it's going to be. But if I look at the Ka, automatically I should know it's going to be weak acid because it's less than 1. When K is less than 1, usually we make very, very little products. All right, so let's look at another one. Let's look at propanoic acid. Let's find its pKa here. Well, we've got the Ka, so all we're going to do is just plug it in. So it's the negative log of the Ka. So the negative log of 1.38 times 10 to the negative fifth, and that's going to give me 4.86. All right, so 4.86. Well, which one is stronger, ethanoic or propanoic? Well, propanoic's pKa is 4.86, and ethanoic, if I look back in the other problem, was 4.74. Well, this one has a lower pKa, so this one is a stronger acid. All right, so with weak bases, we have a different equilibrium constant. It's Kb, but it pretty much means the same thing. So it's the equilibrium constant when a base is ionized in water. Well, a large Kb indicates a strong base. So if it's larger than 1, usually it means that it ionizes almost completely or 100%. So a weak base will not ionize completely. So if I put a weak base like ammonia into water, it's going to make ammonium and hydroxide, but only small amounts if I have a small Kb. So if I'm going to write out the Kb expression, it's products divided by reactants. So hydroxide times ammonium here, divided by ammonia, and I don't include water because it's a pure liquid. All right, so pKb, very similar to pKa, it's just for bases. So anytime we're talking about an acid, we use A. So pKa, or Ka. But if we're talking about a base, we have to use Kb or pKb. So pKb is a way to describe how strong the base is. So the lower the pKb, the stronger the base, and the more hydroxide ions I should have in the solution. So you find it the same way you find the Ka. All right, so if ammonia has a pKb of 4.75, what is its Kb? Well, I don't have to look at an equation, or look at a reaction rather. I can just simply look at this one small equation. I was given pKb, I'm looking for Kb, I just simply plug and chug. So it's 4.75 is equal to negative log of the Kb. So I got a negative, so I got to divide that out. So it's negative 4.75 is equal to log of Kb. Well, remember, you can't divide out a log. You have to actually do the opposite of log, which is 10 to some power. So 10 to this power, 10 to that, gets rid of the log. So you should get a Kb of 1.78 times 10 to the negative fifth here. All right, so now let's look at the next one. All right, so if methylamine has a Kb of 4.38 times 10 to the negative fourth, what is its pKb? Well, just simple problem. I have the Kb. All right, I have the Kb. I can just plug it into this equation. That's Kb. All right, so pKb is equal to negative log of this. pKb is equal to 3.35. So which one is stronger, ammonia or methylamine? Well, methylamine's pKb is 3.35, and ammonia was 4.75 on the last problem. So that means that the smaller one will be the stronger base. So methylamine is a stronger base than ammonia. All right.